Alright, today we're going to be going through some notes in our new notes packet. We're in our new unit, which is talking about gas laws. So go ahead, pop into Schoology if you haven't already, download our notes packet. You'll see it is named 1A, Gas Laws Note Sheet. That's what we're going to be looking at today. Open up onto page 1. The first thing, like we usually start off with, is going to be some vocabulary. Just like last unit, there's a lot of vocabulary in this unit that you need to be comfortable with in order to actually move through the unit. Now, the way we've given you the vocabulary is really just a bunch of definitions on this first page. You can see we have really just short little blurbs about each reading, and we've even gone ahead and bolded the key important things that you should know. So let's go ahead and just read through this really quickly. As we're reading through this, as I have this up on the screen, I'd encourage you start jotting down some notes in this second page, your vocab section. We're going to talk about gas, pressure, atmospheric pressure, volume, temperature, N, and standard temperature and pressure. So starting off, well, a gas, that's a state of matter. Particles move freely, take the shape of their container. We talked about this a little bit in our last unit. Unlike solids and liquids, they do not have a fixed shape or volume. Pressure is the force that gas particles exert when they collide with the walls of a container. Pressure is directly proportional to the number of collisions that occur between the gas molecules and the walls of the container. An increase in the number of collisions results in a higher pressure, while a decrease in collisions leads to lower pressure. It is measured in units such as atmospheres, pascals, millimeters of mercury, and pounds per square inch. And down here you can see all of the different conversions. We will be practicing these conversions later today. Atmospheric pressure is the pressure exerted by the weight of air in Earth's atmosphere. At sea level, atmospheric pressure is 1 atmosphere. As you move to higher altitudes, there's less air above, so atmospheric pressure decreases. This decrease in pressure can have significant effects on the human body and other systems. Easiest example of this is if you've ever gone, say, up high into the mountains, maybe you've had your ears pop. That's just a small little impact of these differences in pressure. Volume refers to the amount of space a gas takes up. It is usually measured in liters or milliliters. Volume of a gas can change depending on temperature and pressure. Think about a balloon with volume. If a balloon is not filled, it has a very small volume. If you fill it up with a gas, maybe helium, maybe air, then that volume increases. Temperature. Temperature measures average kinetic energy of gas particles, just like what we had talked about in our last unit. The faster the particles move, the higher the temperature. Temperature is measured in Kelvin, which we abbreviate with K. At 0 Kelvin, particles are completely motionless. However, this is theoretically impossible. A thermometer measures temperature. To measure the number of times particles hit the thermometer's tip, it needs to be in a closed space. More collisions means a higher temperature. We use Kelvin to measure temperature to make sure all the values are positive. Now, this does have an important relation to pressure. If temperature is how faster particles are moving, well, the faster particles are moving, that means that on average they're going to have more collisions at that higher temperature because they're moving faster. They're just going to be colliding with each other and the walls more. Well, pressure is related to the number of collisions. So if you have a higher temperature, that also means a higher pressure because that faster motion of the particles in temperature leads to more collisions, and more collisions means more pressure. Now, N, that is the number of moles of gas particles. As a reminder, a mole is 6.02 times 10 to the 23rd particles. That's 1 mole. So whenever we see our symbol N, that is the number of moles of gas particles. Standard temperature and pressure, STP, those are specific conditions used in gas calculations when we're referring to 273 degrees Kelvin and a pressure of 1 atmosphere. Okay, so for our vocabulary, take some time add in your vocabulary onto page 1. A lot of this you probably already have a sense for. What we're going to do now, if you have not finished writing down all this vocabulary, that's okay. We're going to move on into some examples converting units. If you did not finish writing down your vocabulary, please revisit this once this video is done to finish copying down and defining all these vocab terms. So, converting units, this is something we've done before, but I do want to kind of rehash, go through a few examples together to make sure we're all on the same page, we're all confident converting units. We got pretty good at converting units earlier, hopefully we still have those skills down. If so, it'll be a really big asset to you in this unit. We're going to go through a few examples for really each different type of conversion. Starting out, we have some conversions that are given to you. For temperature conversions, if you need to do Celsius to Kelvin, you are just going to take your value in Celsius and add 273. If you're going Kelvin to Celsius, take your value in Kelvin and subtract 273. If you need to do Celsius and Fahrenheit, they have a bit of a fancier conversion, but you're still just plugging in one or the other and solving for whatever it is you need. Now, pressure has several different values that you could measure pressure in, and we're going to practice converting. So how exactly do you do this? Well, you are always going to take your given, whatever you're given. So here we are given 6.67 atmospheres. We want to identify, okay, what is this actually measuring? Hopefully we're confident in units of temperature. This, atmospheres, this is going to be a pressure. We want to convert it into millimeters of mercury. Look up at your conversions. You will be given these conversions. They're not something you need to memorize. So how do you actually do the conversion? The key is the units. Start out, write down your given. So we're given 6.67 atmospheres. Please do include the unit. It's really, really important in this unit. You will be losing points if you do not include units in your work and in your answer. We start out with our given 6.67 atmospheres. We want to convert into millimeters of mercury. To do that, all we are going to do is we are going to multiply by a fraction. Take whatever unit you have, whatever your given unit is, and place that unit on the bottom. This is going to cancel that unit out. Place what you are converting to on the top. We're converting into millimeters of mercury. Remember, Hg, that is the elemental symbol for mercury. And now we just have to look at, how many atmospheres for how many millimeters of mercury, and we plug those in. It is 1 atmosphere for 760 millimeters of mercury. Now we can just go ahead, pop this into our calculator, take 6.67, multiply by 760, and we get our answer, 5,069.2 millimeters of mercury. And now there is a space for your answer with units as well. Again, please include the units. You do need that. You will lose points on quizzes, on tests, on check-ins if you're not including the units. It's very important. Let's try one more example. You're starting with your given, 8.7 psi, that's pounds per square inch. 8.7, write down the unit. Multiply by a fraction. The units that you have, the units that you were given, whatever is up here, that gets brought down. PSI, pounds per square inch. The units we want to turn it into, kilopascals, kPa, goes on top. Then we just look up at our conversions. Okay, 101.3 kilopascals. Plug that in. That is equivalent to 14.7 pounds per square inch. At this point, when we multiply 8.7 times 101.3, we also have to divide by our denominator, divide by 14.7. Plug this into our calculator, we find we get 59.95. What are your units? Well, as you're doing this operation, pounds per square inch was on the top and on the bottom. The numerator and the denominator, it's going to cancel, and we're left with just units of kilopascals. Okay, so those are some pressure examples. Let's try some examples with temperature. Let's do an example of Fahrenheit, and we'll also do an example with Kelvin. Liquid nitrogen boils at negative 196 degrees Celsius. Let's convert that into Fahrenheit, okay? Here, we're just going to look up, grab the equation. We are given Celsius. So we want an equation where we can plug in Celsius and get Fahrenheit. So let's grab that. Fahrenheit is 9/5, 9/5, times our degrees Celsius plus 32. So at this point, all we're going to do is we're going to take that equation, and for our degrees Celsius, we're just going to plug in our given value. We're going to plug in negative 196. To do this operation, let's do 9/5. That's our 9/5. This gives you 1.8. Then we're going to multiply that by our negative 196. This will give us negative 352.8. And at that point, we can just add 32, to which we will get negative 320.8. Make sure you include degrees Fahrenheit. All right, now let's try converting Celsius into Kelvin. So for this, we're given Celsius. We want to go Celsius to Kelvin. We're going to use this equation. We can copy it down. Kelvin is just, we're doing number 12. Kelvin is just your temperature in degrees Celsius plus 273. Again, we're just copying that down from right up here. So we can go ahead and plug in, well, what's our temperature in degrees Celsius? It is, 23. We are going to add 273, plug this into our calculator. 23 plus 273 gives us 296 Kelvin. Okay. Let's continue on to our fourth page in our notes, talking about our combined gas law. Here we have a big formula, and at first it might look big and scary, but we're going to break it down and do exactly what it means. It is just a relationship. This is the most important equation we're going to be using really in this entire unit, and we're going to get really comfortable with it. What does it do? Well, it combines the relationship between pressure, volume, and temperature. When one of these variables changes, we can predict what is going to happen to the other variables. Now, one thing is held constant, and this is very, very important, is that the number of moles is held constant. Say we take a balloon, and the balloon has some pressure and some volume at some temperature. And we heat that balloon up, we increase the temperature. Well, we can predict, if we hold that volume of the balloon constant, what is going to happen to the pressure as the temperature rises, using this equation. We just plug in some numbers. But what's important is that in that process of heating up the balloon, what is constant, what isn't changing, is the number of moles, the actual amount of air that is in the balloon. If you let air out, of course that's going to change your pressure, volume, and temperature. We're keeping the number of moles constant during this calculation. Make sure your units match for pressure and temperature. Actually, what I mean to say is pressure and volume. Temperature units should also match, but temperature should always be in Kelvin. Temperature needs to be in Kelvin for this equation to properly function. Pressure and volume, it does not matter what units they are in. Remember, we said pressure can be in all of these different units. As long as pressure 1 and pressure 2, P1 and P2, are the same, it doesn't matter what they are. You just have to make sure that they match. Let's try a few examples. Number 1. Sample of gas occupies 85 milliliters at 750 millimeters of mercury and 295 degrees Kelvin. Calculate the new volume in milliliters at 820 millimeters of mercury and 300 Kelvin. Okay, so what we are going to be doing is we are always going to start out and identify what do we start with and what do we end with. So let's write out a section where we start and a section where we end. Let's bring down our equation. We're just going to copy it down. P1V1 over T1 equals P2V2 over T2. Okay, well, our P1V1 over T1, this is going to be our start. This is what we're beginning the problem with. Then, what we're ending with is P2V2 over T2. Let's identify from what we're given. Well, the sample gas occupies 85 milliliters. Milliliters, that's a volume. So we can write out, okay, the volume we're starting with is 85 milliliters. It is at 750 millimeters of mercury. That is a pressure. 750 millimeters of mercury. And we are given the temperature in Kelvin. 295 Kelvin. We plug this in. 295 Kelvin. Those are all of our starting values. Calculate the new volume. Okay, so what we're looking for is our volume. That ending volume. We do not know what V2 is. That's our unknown. But P2, what pressure is it at? Calculate the new volume at 820 millimeters of mercury. Okay, so our new pressure is 820 millimeters of mercury, and our new temperature is 300 degrees Kelvin. Now this one, we're fortunate in that all of our units match. Our temperatures, again, let's do our check. Temp should be in Kelvin. The temperatures are both in Kelvin. The pressure units should match. We have millimeters of mercury. Okay, we're good to go. When all your units line up, you can just plug into our equation. So what we're going to do, everything we have in our start section gets plugged into the left-hand side of the equation. Everything in our end gets plugged into the right-hand side. Let's go ahead and do this. Maybe we'll do this in purple. Our pressure. We're starting at 750 millimeters of mercury. The volume is 85. Divide by that temperature, 295. Set that equal to, well, the final pressure, the pressure we're ending with, 820, multiplied by that volume, that's our unknown, we don't know what that is, that's what we're solving for, divide by our temperature, which is 300. And now at this point, let's go ahead and grab our calculator. I encourage you, practice plugging this in on your calculator as we're going through. We do have calculators at the front of the room that you can borrow if you need. I like to always go through one step at a time. What you'll find is students will plug in everything all at once. And your calculator can easily make mistakes, or maybe you forget to plug in a parentheses, order of operations gets messed up, and then you get the wrong answer. So what I like to do is say, okay, well, what are we doing here first? Let's slide this over. We're doing 750 times 85. We are trying to isolate v squared. Let's do 750 times 85. Then we're taking this numerator, and we're just dividing by our denominator. Divide by 295. Okay. This gets us a value. Let's go ahead and get this as a decimal. We can write this out. 216.1 equals 820 V2 over 300. We want to isolate for V2. So we want to get rid of this denominator here. Well, how do we do that? We multiply both sides. So our 216.1, multiply that by 300. That gets rid of our denominator right here. Now we need to get rid of our 820 on the top. To do that, we're just going to divide both sides by 820. And we are left with our answer right here, which would be, again, let's get this as a decimal, 79.06. Now, units are important. We started with a volume in milliliters. That means our volumes have to match. So our ending volume is also in milliliters. Let's try our last two examples here. A sample of gas has a volume of 9.5 liters at standard temperature and pressure. What will the new volume be in liters if the pressure increases and the temperature increases? Okay, so identify our start and our end. We will start out with V1, P1, T1. We will then have V2, P2, and T2. Okay, the sample of gas has a volume of 9.5 liters. That's what we're starting with. 9.5 liters. Careful with our units. At standard temperature and pressure. Look back. Find standard temperature and pressure. This was all the way back in our reading. Standard temperature and pressure, right up here, is a temperature of 273 Kelvin, 0 degrees Celsius, and 1 atmosphere. So that is pressure 1 atmosphere and 273 Kelvin. Remember, we always need to plug in our temperature in Kelvin when we're using this equation. Then, we are asked, what will the new volume be? So again, we're solving for volume. If the pressure increases to 3.25, so now our ending pressure is 3.25 atmospheres, and the temperature increases to 310 Kelvin. Okay, same process. We're just going to plug in to our equation P1 V1 over T1 equals P2 V2 over T2. We'll go ahead and we can write out, let's get our calculator out of here for the time being. Our first pressure is just 1, then our starting volume 9.5, plug in our temperature, 273 on the denominator, then we have our pressure, 3.25 times that volume, that's what we're solving for. On the bottom, we plug in our ending temperature. And now, let's bring out the calculator. .5 divided by 273. We're going to multiply by 310 and divide by 3.25. At this point, once you've done all the heavy lifting, once you've figured out all your variables and plugged in, the heavy lifting is really done. At this point, it is just converting and doing some math. So at this point, it's just algebra. If you need any help with this, please swing by the ARC. There are lots of student tutors available to help you. I'm also in the ARC 4th hour. Please swing by really any available time. Stop by. I'm happy to help go through the algebra, how we're getting our answer here. But plug this all in. As you can see, our answer, our volume, 3.32. Double check your units. What units of volume did we have to start with? We had liters. So that means this answer is going to be in liters as well. Okay. Last example. you can see how really each time we're going to start off with your starting and ending values. You're going to record all the information that is given to you and plug that in to solve the problem. So let's see, what are we starting with? Sample of gas is occupying 4.2 milliliters. The pressure, 1.25 atmospheres. The temperature is 30 degrees Celsius. All right, what will the new temperature be if the gas, and this was our starting values, let's get our ending values. The ending value for our volume is 4.5 liters, and the ending pressure is 1.1 atmospheres. We need that new temperature. Okay, few things should go off in our head. Let's look at our rules. Temperature needs to be in Kelvin. Units of pressure and volume need to match. Well, pressure is fine. They're both in atmospheres. What is not fine is our volume. We have on one side milliliters, on the other liters. It doesn't matter what unit you actually use. It just matters that they both match. Recall from last unit, 1,000 milliliters is 1 liter. You'll have to do some unit conversion. Let's go ahead and turn 4.5 liters into milliliters. So to do that, start with your given, just like we practiced up above, 4.5 liters. Multiply it by a fraction. Take the unit you have, the unit you're given, the one you want to get rid of, and put it on the denominator. Take the unit you want, in this case that's milliliters, put it on the numerator. Then fill in your conversion. It is 1,000 milliliters for every 1 liter. So 4.5 liters is going to be 4.5 times 1,000, 4,500 milliliters. Okay. At this point, we can go ahead and write in as a little substitute. This is 4,500 milliliters. Now our volume matches. We have milliliters on one side, milliliters on the other. This is good. But we need our temperature in Kelvin. Cannot be in degrees Celsius. So we need to convert our temperature in degrees Celsius into temperature in Kelvin. Now, let's go up, grab our equation. Again, as you're doing problems, as you're working on the homework, it is okay to not have all these formulas memorized. What you should do, have your notes open as you're going through our practice problems. That way you can reference these equations, and the more you use them, the easier they're going to come, and the more you're going to start to memorize them and have to look back at your notes less and less. So, to get Celsius turned into Kelvin, we are going to say that Kelvin is just Celsius plus 273. So, our temperature in Kelvin is the temperature in Celsius plus 273. So let's plug in that temperature in Celsius. It is 30 degrees plus 273. That gives us our temperature in Kelvin. Pop this into your calculator and you find that this would be 303 Kelvin. So let's go ahead and write this up here. 30 degrees Celsius is also 303 degrees Kelvin. Now, all our units match up. Everything is as it should be. We can plug in to our equation. And P1 V1 over T equals P2 V2 over T2. You go ahead, substitute in. Our P1 value is 1.25. V1, 4.2. T1 is 303. That is equal to our new pressure value of 1.1. Our V2 value, our new volume, 4,500. And that new temperature that we're solving for. Now to solve this, it's going to be a little bit trickier. Again, this is an algebraic process going through. What I would encourage us to do, since we have that denominator, let's flip temperature up to the numerator. To do that, multiply both sides by T2. This is going to give us T2 times 1.25 times 4.2 all over 303 equals 1.1 times our 4500. This is a little bit easier to solve. We can do 1.1 times 4500 multiply by 303 divide by 1.25 and divide by 4.2.